Hello everyone, Mr. Fawcett here, and we are about to start the last lesson of this section. It is on biconditional statements. Before we get there, let's do a couple review problems, 3 to be exact. For numbers 1 and 2, you need to write the conditional statement for each of those statements, so turn them into a conditional statement. For number 3, you're going to write the converse of the conditional statements already given, and then determine whether the converse is true or not. So pause the video, take some time to work out those 3, and then come check your work. All right, so I put the answers up in bold. For number 1, the statement is the intersection of 2 lines is a point. So if we turn that into a conditional statement, an if-then statement, we have if 2 lines intersect, then they form a point. Number 2 says an odd number is 1 more than a multiple of 2. So again, turn this into a conditional, and we can say if a number is odd, then it is 1 more than a multiple of 2. Number 3 is a little different because we're given the conditional. The conditional is if Pedro lives in Las Vegas. I should say if Pedro lives in Las Vegas. A little typo there. Then he lives in Nevada. So the converse here would be if Pedro lives in Nevada, then he lives in Las Vegas. So clearly the conditional statement is true. All right, this is true. If you live in Las Vegas, it's impossible for you to live anywhere else but Nevada. I guess actually we should. We're going to assume that we're only talking about the Las Vegas and Nevada. There could be other cities called Las Vegas. I guess I'm not aware of them, but that's a possibility. The converse, though, if Pedro lives in Nevada, then he lives in Las Vegas. Well, he could live in Nevada, but not live in Las Vegas, right? He could live in Pahrump, or he could live in Boulder City, or he could live in some other town or city that's not Las Vegas. So while our conditional was true, the converse here is going to be false. Okay, let's jump into some of the new content for today. Let's bump this up so we can see it. There we go. So a biconditional statement. A biconditional statement can be written in the form P if and only if Q. So this means 2 things. It means if P, then Q, and if Q, then P. So our biconditional notation is this double-sided arrow. So it means that P implies Q, but also that Q implies P. For a biconditional statement, the original statement and the converse will both be true. Again, this is only for a biconditional. For a regular conditional statement, sometimes the converse ends up being false, even if the original statement is true. And then another little notation here, sometimes instead of saying if and only if, we can abbreviate that with a if with 2 F's. So you're free to write whichever one you want. Just make sure if you go with the if with 2 F's, you actually include the 2 F's. So our example over here says that a solution is an acid if and only if it has a pH level less than 7. So this means that 2 things have to be true. Right? We have this first statement, so this would be like our P implies Q. So if a solution is an acid, then it has a pH level less than 7. But then we also have a Q implies P, the converse. The converse also has to be true. So if a solution has a pH level less than 7, then it is an acid. So that is what a biconditional is. It means that the original statement is true as well as the converse. All right, let's do some practice. So it says write the conditional and the converse for each biconditional statement that's given. I'm going to let you guys do that for numbers 1 and 2. We will hold off for number 3 because that's a little bit different. So pause the video, try numbers 1 and 2, and then we'll come back and check solutions. All right, so for number 1, the biconditional statement says a solution is a base if and only if it has a pH level greater than 7. So our conditional statement would be if a solution is a base, then it has a pH level greater than 7. The converse would be if a solution has a pH level greater than 7, then it is a base. And again, for biconditionals, both of these will always be true for a biconditional. Okay, our second biconditional statement says an angle is obtuse if its measure is greater than 90 degrees but less than 180. And we have the double F here, so that really means if and only if. So it does mean it's a biconditional. Conditional would be if an angle is obtuse, then its measure is greater than 90 but less than 180. The converse would be if an angle's measure is greater than 90 but less than 180, then it is obtuse. And again, both the conditional and the converse must be true here. And you can think about that, especially for the math one. Maybe you're not familiar with bases and acids in science or the pH scale, but certainly we're familiar with obtuse angles. So the conditional statement, if an angle is obtuse, then its measure is greater than 90 but less than 180. Well, that makes sense, right? Because it's just based on the definition. And the converse, if an angle's measure is greater than 90 but less than 180. So pick any number between 90 and 180, and you're going to get an obtuse angle, right? So the converse is also true. All right, let's go down to number 3. So for the following conditional statement, write both the converse and the biconditional statements. So here we're just given the original. I want you to write the converse and then transform the original statement into a biconditional. And then we'll talk about whether the biconditional is true. All right, so our conditional statement says if 2x plus 5 equals 11, then x equals 3. The converse, if x equals 3, then 2x plus 5 equals 11. The biconditional, 2x plus 5 equals 11, if and only if x equals 3. So let's think about whether this biconditional is true. For the biconditional to be true, then both the conditional and the converse must be true. So is the conditional true? Oops, let me get out my pen. So the conditional says if 2x plus 5 equals 11, then x equals 3. Well, we could solve that, right? It might be clear to you what the answer is, but subtract 5 from both sides, I get 6 on the right-hand side, divide by 2 on both sides, and I get x equals 3. So yes, if we have that equation, then x must be equal to 3. The converse, if x equals 3, then 2x plus 5 equals 11. Well, if x is equal to 3, and we substituted 3 into this equation, then it would be true. So if the conditional is true, the converse is true, then the biconditional is also true. And that's what we're going to finish up with today with the rest of our practice. We're going to be testing the value, the truth value of the biconditionals. Okay, so we just talked about this, but for a biconditional to be true, both the conditional and the converse must be true. And if either of those is false, then the entire biconditional is going to be false. So that's what we're going to look at for this next section. I give you a biconditional. So just for number 1, there's our biconditional. You're going to write out the conditional. You're going to determine whether it's true or false. If it's false, give a counterexample. Same thing for the converse. Now, if either the conditional or the converse is false, then we will say the biconditional is false. If they're both true, then we can say the biconditional is true. So you have 3 problems to work on, 1 on this page and then 2 on the other page. And then we'll go over probably 1 or 2 of these to finish off this video. All right, so number 1 says a square has a side length of 5 centimeters if and only if it has an area of 25 centimeters. So our conditional statement is if a square has a side length of 5 centimeters, then it has an area of 25 centimeters. Well, this is true if we have a square and one side is 5 centimeters, then every side is going to be 5 centimeters, right? And area is length times width. For a side, it would just be a side squared. So our area does become 25. So this is true. The converse says if a square has an area of 25 centimeters squared, I hope I said centimeters squared up there. I should have. Then it has side lengths of 5 centimeters. So this time we're working backwards. We know that the square has an area of 25 centimeters squared, or square centimeters. Then we need to figure out the side lengths. Well, if all sides have to be the same, right, and the area of a square equals a side squared, well, we get 25 is equal to s squared, and we get 5 is equal to s. We can't have a negative value because we're talking about side lengths. So this is also true, which means that our biconditional is true. If our conditional is true and our converse is true, then the biconditional itself will be true. Okay, we're going to skip number 2, and we're going to go down to number 3. I think that's a slightly more interesting one. Again, if you haven't done this already, pause the video, try it on your own, and then come back. So our biconditional says a rectangle has side lengths of 12 feet and 25 feet if and only if its area is 300 square feet. So conditional is if a rectangle has side lengths of 12 feet and 25 feet, then it has an area of 300 square feet. Well, if it is side lengths of 12 and 25, we'd multiply length times width. Area equals length times width. So our area is equal to 12 times 25, which is equal to 300. Okay, so that checks out. That is true. Let's look at the converse. If a rectangle has an area of 300 square feet, then it has side lengths of 12 feet and 25 feet. Well, let's test that. If its area is 300 square feet, do our side lengths have to be 12 and 25? For a square, the side lengths always had to be the same, right? Because all sides are the same. But for a rectangle, that's not necessarily the case. Are there other options for what the side lengths could be? And you could play around with this, but it may be easy to tell that the side lengths could be 10 and 30, right? 10 times 30 is equal to 300. We could also have side lengths of 15 and 20. We could also have side lengths of the square root of 300 and the square root of 300. Right? You could think about that a little bit, but the square root of 300 times the square root of 300 gives us 300. So this converse is false, which means this biconditional is false. Because again, the conditional and the converse would have to be true for a biconditional to be true. All right, that ends this video and this section of lessons. Next time we come back, we will be looking into how to write a 2-column proof. So again, starting a new chapter of math that you may not have looked at up until this point. Proofs, they're exciting, they're challenging, but they can also be a lot of fun. So I look forward to seeing you next time. As always, enjoy the rest of your day.